Right now we have Russell Currey, who will be talking about an abridged history of Linux kernel hardening. So let's welcome Russell to the stage.
All right, thank you very much. Yeah, hi, I'm Russell. It's great to be here. It's my first BSides. It's been awesome so far. Today I'm going to be talking to you about the Linux kernel and how it kind of grew up over time. Linux has come a very long way, and there's been many bumps along the road, but you kind of get to see a hobby project become the thing that runs the world, one mistake at a time. About myself, so I've spent the last 8 or so years as a Linux kernel developer. For about half of that, I was working on kernel hardening, kernel security for IBM for their Power CPUs. And as of a week ago, I'm a researcher at InfoSec, so I've done blue team stuff, red team stuff, which is good because my favorite color is purple. So just to quickly break down what the title actually means, the word abridged does a lot of heavy lifting here. So this is not going to be a reference material. It's more of, here's an excuse to talk about all these cool things that went into the kernel. The big caveat is that I wasn't around for a lot of it. Linux first existed publicly in 1991, where I was busy not being born. So, and then as time went on, I didn't really get involved with the kernel until around 2015. So a lot of this is kind of, retroactive. The word history also is quite questionable, given I'm only actually talking about things that happened after 2007. So just don't worry about anything before that, it doesn't really matter. History also finishes somewhere around like 2020. So if you want to know about the really current stuff, there's a talk tomorrow called Modern Linux Kernel Mitigations that'll talk about the things that have recently come in or are soon coming in that not all distros enable, etc. Everything we're talking about today is pretty bread and butter. You will probably encounter these on any modern Linux system, with the exception of some niche architectures. Most of the things I'm talking about today have architecture-specific implementations because they're memory management-related things, so the MMU needs its own implementation. And the Linux kernel itself, why is the Linux kernel so important as a thing to secure? If you compromise some box, if you get a foothold and you want to get a privesc, the kernel is probably not the thing you go looking at first. It's quite difficult to compromise relative to the billion random things running in user space. But the big thing that the Linux kernel has going for it as an attack target is that it's prolific. It's on every Linux machine, after all. So if you do your due diligence and Google the kernel version and see if there's anything on exploit DB, if there is something, then you've won by default. The Linux kernel it's everywhere. It's very prolific in all different kinds of devices. Android phones, most servers, yada, 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 most embedded devices. So if the kernel has security problems, then the world has security problems. Another reason that it's so important to focus on its security is that it is very, very difficult to prevent bugs in the Linux kernel. It's a gigantic code base. It moves very fast. It does a ton of things. There's new contributors all the time. It runs on hosts, on guests, in between. It's a hypervisor on all these different architectures, different configurations. Every distro basically has their own complete fork of the source code, yada, yada, yada. So it's a big, difficult project, which means it's hard to secure, so it's important to try and do a good job of it. And the idea of hardening the kernel is about self-protection. And I've tried to explain this to people, and they're like, why would you protect a code base from itself? How does that make any sense? Why don't you just not write bugs? So you try getting tens of thousands of random people around the world writing C to not write bugs, and let me know how it goes. Bugs are inevitable. There's always going to be bugs in the Linux kernel. There's no way around that. Even if it gets rewritten in Rust, there will still be bugs in the Linux kernel, despite what some people will tell you. So kernel self-protection is really important. So just to run some ground rules, I'm going to be talking mostly about technology, about what went into the kernel, rather than so much of the politics around why and who and all of that kind of stuff. On that note, I'm going to be talking about what went upstream. So not all, in fact, a lot of Linux security stuff wasn't initially developed upstream. The concepts didn't come from upstream. They came from other projects, like GRSec is probably the most notable one. But given the majority of the developer population focuses on Linux, all the distros we use flow downstream from mainline Linux. We'll be talking about when things went upstream in the form they were in when they were upstreamed. And just to underline that I'm talking about the kernel itself. There's security features in the kernel that are actually just the kernel enabling things to happen in user space. And that happens all the time, but we're not interested in that. Not going to be talking about SE Linux, etc. So focusing on the kernel protecting itself against attacks rather than exposing things to user space to do the same thing. So kernel hardening or kernel self-protection. You might also see KSPP, which is the kernel self-protection project. There's a Linux hardening mailing list, etc. Things that happen in that kind of a space. So here are the things that happened in history. We have the prehistoric era, basically, the before times when Linux was a hobby project that had the unfortunate incident of running all the world's businesses. The formative years where people kind of started to accidentally realize that security is a problem and tried to start doing something about it, often inadvertently. The period in which things started to get a bit more serious, so vendors, CPU vendors are now doing things related to security. And then kind of entering modernity where there's a much greater focus and there's a lot of external to the upstream community projects that are having a big influence on Linux. So that is what history is. Let's talk about it. And in the olden days, again, I was busy being in primary school or whatever, but there isn't a great story for security in Linux. There isn't really a centralized reporting mechanism. There's open security bugs that have been reported that get fixed years later. Security is a very distant thing from developers' minds. Tooling as well is quite poor. So nowadays we have static analysis. We have much better compilers. We have a lot of tooling inside and outside of the kernel that helps us find problems. None of that. So there's a few quotes here that I think tell an interesting story. Here's one from the early days, which is this guy complaining that the problem with Linux is there's just too many people hacking the code. It's reached a complexity where the I hack quickly some code approach doesn't work anymore. And this is kind of an inflection point in which Linux as a hobby project for random people to vomit their code into isn't really going to work when we're relying on this to run the world. Code standards have improved over time. Our ability to test has improved over time. Our thoughtfulness for what we put in the kernel has, but depends on the subsystem. Here's a quote from Spender, who's very iconic in the kernel hardening space. 12 new CVEs from just one guy with grep in a few days in his spare time. So low-hanging fruit, I'm not sure if that actually describes it. It's probably worse than that. Security is just not a strong consideration. It took a long time as well, not just on the technical side, but in terms of a project structure to have a central reporting mechanism for security issues to properly kind of iron out what the relationship between upstream and distributions is. Those in the know will know that war rages to this day. And a general sense that, like, who cares about security on Linux when the thing next to you is Windows? If it's 2005 and your mum's got a virus again because she downloaded a Dolphin screensaver, then you're not really thinking about your security problems on Linux. So a general sense in the community, allegedly, from the people I asked that were there, because I was busy being in primary school, that Linux just didn't have the security focus because Windows was just this gigantic dumpster fire next door. So at what point did things start to get better? Well, let's have a bit of a look at that. So 2007 is where history begins, famously. So it's Linux 2.6.15. The 2.6 thing will go for a while. Don't worry about it. Someone thought it was a good idea. For context, I've just started grade 9. So I was very on top of kernel security in these days. I definitely knew what that meant. If you want to know how long 2007 is, or if you want to feel old, everyone was wearing this shirt. I don't know how many of you remember this, but it was quite. Does anyone still have one? Raise your hands if you still have one of these shirts. Anyone? Yeah, probably for the best. Anyway. And so the kernel community is about to have a really hard look at what read-only means. Now, I'm not a linguist, right? But I would infer that read-only means that you can only read. That would kind of check out, right? So what does read-only mean? Well, you have the Holy Trinity, the three horsemen of the apocalypse. Wait, isn't there four? Anyway, it doesn't matter. Three musketeers, that sounds better. Of read, write, and execute, your fundamental permissions. You have these on files, you have it on memory. And so memory permissions come down to which combination of these you have. And if you get it wrong, then one could say that there are consequences. If you compile a binary and you look at the sections in the output, so this is just some rando elf. We've got text, which is code, and we've got data, which is data. And you can see you've got some things here, like your text is read-only, which is what you'd want. You don't want people to be able to overwrite code. Your read-only data is in its own section, which is separate to the not read-only data. But ultimately, when you load this, there's nothing magical that says, well, it was in an elf section, so it has to be secure. You need a memory management unit in your CPU to actually enforce these things. If you want your read-only data to be read-only, you have to tell your MMU that, and your MMU has to be able to do that. So you could think, okay, cool, he's about to tell me that they realized this was a security problem and that you should actually have sensible permissions on your memory. Well, no, they didn't really do that. So this came along in the form of config debug RO data. So it's not a security feature, it's a debug feature. And it was described as mark the kernel read-only data as write protected in the page tables in order to catch accidental and incorrect writes to such const data. So the concern is not our entire memory space is RWX. The concern is like, well, if you screw up your code, this can like help you find out why. And so it would still be quite some time from this point to where people actually turn this on. And then fast forward to today where it's ubiquitous. On many architectures, you can't turn it off. So the way this actually works is that after kernel init, so the kernel has functions that only runs during early boot. In the init section, it will do all its init stuff, and then it'll just get rid of that stuff. It just jettisons it. And after that point, it marks read-only data read-only. And there's perks to doing it this way, because you have like annotations in the kernel source where you can say read-only after init, for example, on a variable. And so basically, you hit this mark RO data RO, which does what it says on the tin. It goes to the MMU and it says, please mark this stuff read-only. And so yeah, this was a debug feature and not a security feature. Nowadays, we know it as strict kernel RWX. It's also called kernel memory protections. If you're on some niche architecture that doesn't have this, you get this big bold text in your D message saying, this architecture does not support kernel memory protections, in which case you should cry. And this is very ubiquitous now, and it just enforces the fundamental rules on your core kernel. That code in the text section should be readable and executable. Data that is not read-only should be readable and writable, and read-only data should be read-only. So the concept of read-only being read-only came along quite late in Linux's lifespan, and still no one turned this on for ages. So it's still we're not looking too good yet, but that was the state of the world in 2007. So do things get better in 2008? Well, kind of. We're still doing the 2.6 thing. Very important year, 2008, because I became a Linux user. So my first distro was Ubuntu 8.04, back when they were doing the orange-brown thing that they grew out of. This was the glorious era of wobbly windows and like the eyes thing you had on your panel that followed your cursor around. The 3 people who believe in the year of the Linux desktop, like, yeah, man, I remember that. So very iconic kind of thing. And this is the point at which the first support for stack canaries happened. So this device I've got a photo of here is a canary resuscitator. And it's a good example of the hacker spirit, I think. So this is a device from coal miners who, having some amount of morality, felt bad for the canaries that they were sending off into the murky abyss, and developed this canary resuscitator to bring them back to life. So canaries are cool, and the kernel finally got them. So stack canaries are probably a reasonably common concept. And it marks a pretty important milestone, I think, in being one of the first major compiler features that ended up being used in the kernel. When toolchains get new support for security features, it's often quite challenging to turn them on in the kernel. It often takes additional work. The kernel is not really written in C and ASM. It's kind of written in GCC garbage. It's kind of written in weird GCC hacks. And the kernel and GCC evolve alongside each other and pile jank on top of jank. They're very hard to separate, to the point where for Clang to compile the kernel, they basically had to port a bunch of GCC garbage. So it's not always easy for a new kernel, for a new compiler security feature to be turned on in the kernel. Plus, it usually degrades performance, which means you're not allowed to turn it on. So we now have a nice compiler feature here, and the concept is reasonably simple. If you have something like a buffer overflow that allows you to write into the stack, and you can just achieve whatever code execution you want by blowing over the return address. So if you blow past your buffer and you overwrite some stuff and you put a pointer at the return address, then your function returns and you jump to the place that you've inserted. Having a canary in there inserted by with instrumentation inserted by the compiler means that you can no longer overwrite that without also figuring out what the canary is and putting the same value in place. You can no longer just trash that canary, because if you blast over the canary, then it'll blow up. So this is, again, some pretty basic stuff, but it took quite a while for things like this to happen. This is known as config stack protector, and there's like stack protector strong or whatever. So making some headway. So continuing on here into 2010, apparently 2009 didn't happen. It's not really important, really. Still doing the 2.6 thing, so that's regrettable, but we'll trudge on through. I really hope no one here still runs one of these in production. I'm about to show you something disturbing. So this is my senior year of high school. I showed this photo to people, and they say they look like Jim from The Office. I don't know how accurate that is, but to each their own. So we haven't talked about modules yet. So kernel modules are a big part of the kernel. So they are dynamically loaded. So they can load at boot when your kernel detects you've got certain hardware. It'll load some modules in. They can be dynamically loaded. If you go to spin up some kind of network interface and you don't have the module in yet, it can auto-load. You plug in a new device, yada, yada, yada. So they have their own separate virtual address space. They live entirely inside the kernel's virtual address space. And at this point, there's still nothing enforcing that they have sensible memory protections. They still have read, write, execute on everything. Because what was done for the kernel text wasn't done for modules. It's a different memory space. So you would think it's several years down the track. People have learned something, and this is going to be a security feature. No, it has the lovely name debug set module ronks. I know it's read only, no execute, but come on, ronks. It's a lovely word. Which implements the same thing as debug RO data, but for dynamically loaded modules. So enforcing that code is readable and executable, data is read and writable, read-only data is read-only. And in the spirit of good namings, it was going to be renamed to hardened module mappings before finally becoming strict module RWX. So it's like the companion to strict RWX. It's a bit more difficult to implement. Quite a bit more difficult to implement than strict kernel RWX. I know because I wrote it for power. So, but we're making some progress here. We're starting to get some sensible memory protections at least. So at this point, things are getting a bit better, but still we're not really thinking about security here. So Linux 3.0, a very, very, very big achievement. I've seen people from outside Linux ask what is up with the versioning. The answer is it's whatever Linux feels like. And nowadays, the way that major version numbers increase is the leftmost number goes up when the rightmost number exceeds Linus's amount of fingers and toes. The concerning thing is that we've had a .20 and then it increments, but we've also had a .19 and it increments. So I'm not sure what the state of his fingers and toes are, but perhaps we should be concerned. So we haven't talked much about user memory yet and what distinguishes user memory and kernel memory. Things you would not really want to overlap and have issues with. So user space and kernel space share the same virtual memory. So you're in the same you have different ranges, but ultimately, you're dealing with addresses in the same way. And so if you don't have isolation between user memory and kernel memory, then you have problems. And this is not universal across architectures. There are architectures that have completely separate memory spaces. I think S390, or that's IBM Z, the mainframe architecture, they just have completely separate spaces for user pointers and kernel pointers, but that's quite rare. So if you don't have this level of isolation, then attacking the kernel is really easy, because if you can just bamboozle it into reading from some user pointer or executing from some user pointer, you don't even need to do anything in the kernel. You can just point at what you've already done in user space. So even though they're logically very different concepts, if you need some way to enforce the barrier. Again, from before, if you don't have any kind of protection here, then if you blow some stack in the kernel, put a user address there, then you're done. There's nothing further to do. So as you can probably guess I'm leading up to, there's going to start being more enforcement of these kind of barriers. And it marks a pretty important moment in kind of the history of Linux security and operating system security in general, which is that it's not just people on the software side thinking about this stuff anymore. It's silicon vendors. So chips are being made with more and more memory protections in them. It's becoming becomes a competitive advantage for chip vendors. And we're getting more and more MMU features that let operating system developers do smarter things. There's a lot of things that you can theoretically do in software you don't need hardware support for. And if you want to have some ultra-hardened user space program that's very slow, that's fine. But I've put security mitigations in the kernel and then got bug reports for 0.5% micro-benchmark regression. So it's really hard to justify doing things if they cost performance. And hardware features are the main way to get around that. If the hardware vendor can have some hardware-accelerated mechanism to be able to do these kind of enforcements, and that's the realistic way in which they get included. And then, also they can advertise that, we're more secure and yada yada. So this is where we first got SMEP, or Supervisor Mode Execution Prevention. On different architectures, it has names like PXN, which is Privileged Execution Never. But basically, you just set a bit in whatever magic register it is for your architecture, and the CPU will no longer allow the kernel to execute from a user address. So if you do bamboozle the kernel into trying to execute user space code, it just won't work. It'll blow up. And you might have seen this. You'll get like a kernel error. You'll get a log, and it'll be like exploit attempt ? So if you ever see that in your kernel log, then you should, in fact, be concerned. And this is quite a significant bar raise in terms of the difficulty of getting an exploit to work. A lot of these kind of hardening features and protections don't eliminate it being possible to compromise the kernel. They just make it more difficult. And the more difficult you can make it, the more sophisticated an attacker has to be, the more things they have to change together. Even if it just makes them take more time from step A to step B, that gives people more time to patch the issue or whatever. So the harder you can make these things, the better as a defender. So now we've raised the bar quite a bit. If you have some shell code you want to execute inside the kernel, you can't just trick it to looking at user space anymore. You have to try and find some way to get your shell code into the kernel memory and then execute it from there, which leads us to 2012. So we have sane version numbers now, well, for some definition of sane anyway. 2012, the world ended. I can prove this because I was at uni. I was my first year of computer science at uni. And I met a girl, and I told her I used Arch Linux, and she was actually impressed and didn't just roll her eyes and walk away. And there's no way that can happen outside of a simulation. So very famous image here that we always link to my friend that works at NVIDIA. So if you've heard a little bit about the relationship between NVIDIA and the Linux community, just know that over a decade and nothing has changed. So we're going to be talking about accesses to user memory now instead of execution. So read and write. And unlike execution, access to user memory is a necessary evil. It happens all the time. Most of your syscalls and whatnot, you're giving the kernel something to do. You're passing it some data. You're getting some data back. So reading and writing the user memory needs to happen. It happens all the time. I don't think there's any justifiable case where you should be executing user memory, so that one's kind of cut and dry. But you need to be able to do this. You can't just unconditionally turn this off. And again, if it's a very powerful primitive to be able to get either to get corrupted data or shellcode or whatever into the kernel memory. Also, leaking secrets out of the kernel is also a big problem. So we want to only have the user space accesses from the kernel that we like. We want to have our cake and eat it too, essentially, which is where SMAP comes along, or supervisor mode access prevention on x86. On ARM, it's called PAN, or privileged access never. Basically the same thing as SMAP, except in this case, you can't just unconditionally turn it on. So we do need to be able to do this. And the way it works is basically that it just gets swapped on and off all the time, which leads to its own bug category. So when it comes to user accesses, very thankfully, the kernel has these copy to user, copy from user functions. So the kernel isn't just doing raw reads and writes from user pointers. It's going through these helpers. So you would go into copy to user, and you would enable user access, do all your things. Hopefully you're not preemptible, and then turn it back off, and you're fine. So it is quite a bit more complex than SMAP to implement. Maybe I'm overselling that. The reason I think that is because I wrote this for Power, and I got it pretty wrong. The maintainer only rewrote like half of it. It wasn't really that bad. Who knew nested interrupts were a thing? Anyway, it doesn't matter. So the origin story of these copy to from user functions is really interesting, and it's quite fortunate that Linux has these, because imagine not having these. Imagine trying to implement SMAP without having dedicated accesses. Imagine having to go through your entire operating system and replace every single direct read or write with a helper. That's a pain, and that's why Windows doesn't have SMAP, and basically every other operating system does. So these were present right from the get-go, right from 1991, when I was busy being not alive. Linus Torvalds, as part of the reason Linux was a hobby project for him, was he was experimenting with all these i386 features, and some part of that led him to have these helpers to always do something for some optimization or whatever when reading and writing from user space. So that had the follow-on effect from that to the ability to make the Linux kernel more secure is genuinely enormous. So turned out quite well. So continuing on through history to 2013, version numbers sane. Linux was busy winning Jeopardy. I don't know how many people know about this, but this is IBM's Watson AI thing on Jeopardy with Ken Jennings and the guy who's not Ken Jennings. I don't know who that is. So this is running on like a big data center full of, I think, Power 7s. So Linux won Jeopardy. Still has trouble sharing my screen, but it can win Jeopardy, so that's great. And so this is where we had the introduction of KASLR, kernel address space layout randomization, or KASLR. And if you've done much binary exploitation, you're probably quite familiar with ASLR. Your stuff is now everywhere, and you have to try and figure out where it went. So the idea that you can randomize where things are in memory means that in order to mount some attack, you need to figure out the locations of the objects you're looking for. If they're at fixed offsets, then it's quite a bit easier. So this is when this came into the kernel. It is quite complicated to implement as well. And I think that KASLR is also an interesting inflection point, because I think this is the first time that for the Linux community, a security feature came along that made their lives a genuine living hell. So before this, if you're trying to debug something, your pointers are just your pointers. You have, in printk, you have all these different function, what are they called, the string replacement thingies in printf and printk. Instead of being able to see your pointer to figure out what's going on, you get an under pointer val under. You now have to go through every single point at which anything is printed in the kernel and try and figure out if we're ever leaking the location of anything. In order for KASLR to be effective, you can't have info leaks. Any info leak that reveals the location of something in the kernel is now a security vulnerability, which is a big pain. If you're debugging some issue, you might not be able to just turn Kasler off and run it again, you get a report from someone, and they spit out the thing, and you're like, okay, great. I can't wait to figure out what all that means. The kernel, as I mentioned before, the kernel's big, complicated. Mistakes are easy. Info leaks happen all the time. So the effectiveness of Kasler is quite complicated. And if you look up, there's a lot of different analyses of the effectiveness of Kasler out there. And it is effective as a bar raise. It does make things more complicated. But the value of ASLR in user space can't really be compared to the value of KSLR. A lot of reasons are just size and persistence. User space programs run all the time. It is much easier to get an info leak out of Linux. So a lot of the things that made ASLR an effective mitigation in user space struggle to hold up at something at the scale of the kernel. So it is an effective bar raise, but it's a bar raise that people tend to get around anyway. It's rare that KSLR would prevent a full attack. If you've found some cool Linux exploit, you can probably find multiple KSLR defeats to go along with it. So it's not to say it's not useful, because it is, and there's been attempts later down the line to expand KSLR and make it more useful. It is definitely still something you should have on, unless you're debugging. But it's not the slam dunk like a lot of these other things, and it had a pretty significant impact. You still see people complaining about this. It really did kind of change the way people worked in the Linux kernel. So continuing on with our story, we ran out of digits, or Linus did, so we've gone up to 4. What year are we on? 2015, yes, very important year, 2015, in which the Linux kernel got irrevocably worse because my first patch got in, so there's my first commit. I don't have any clue what that patch does, but it doesn't really matter. It's still in there, I think. And so this is where we got our first sanitizer, and this is going to be a continuing trend. We've mostly been talking about features in the kernel itself that run to actively protect it, and ksan doesn't do that. Ksan's a sanitizer, so built on top of asan, which you might be familiar with from user space. Ksan's a dynamic memory safety error detector, and so it's not something that distros don't turn ksan on, right? It has a performance impact. It has some false positives sometimes. But if you're trying to figure out what's going on in some code, if you're trying to test to see if there's memory safety issues, having a tool like this you can build into your kernel and enable and run, and actually have an idea of what's going wrong with my allocations. Are things going out of bounds? Am I use after freeze, double freeze, yada yada? Being able to actually have something automatically find these things and report them to you is a really powerful tool. It does this by having a shadow memory region where it records and tracks allocations and then compares them. And so I found this number. The sources are trust me, bro, but I swear I found this number in a few different places. Around 70% of security issues are memory misuse bugs. I totally found this from some credible sources. You'll just have to believe me. So being able to find memory misuse bugs is very good for kernel security. And as the kernel code base gets smarter, it's not just about protections, it's also about tooling. So here's some memory corruption, and you get this nice thing out of having ksan on. So it says, this is the address, it's in this cache, it's at this offset, it belongs to this page, which is very good if you're a developer, because memory corruption is one of the hardest things to debug. So memory corruption is cursed, and this is kind of a random tangent, but I feel like it's important how much you know this. Memory corruption is the worst thing in the world, because the problem is that if you have memory corruption and you crash, you're having a great time. If you can figure out what's going on at the point at which the memory corruption happens or not long after, you've saved yourself months of pain. If you crash and you don't know why, at least you've crashed, but it's when bad data propagates that everything is horrendously cursed. Because if you have some kind of memory corruption and then weeks later you crash for some reason, the thing that made you crash is going to be very far removed from your actual memory corruption. So in terms of the general sanity and stability of the Linux kernel, having tools like this that can actually let us know when things are going wrong are really important. So carrying on to 4.4 through to 4.9, and this is when the entire way that the kernel stacks work changes. So in 2016, we first got VMAP stack, or virtually mapped kernel stacks. So Before this, the kernel's own stacks were allocated on physically contiguous memory. If you have some kind of buffer overflow, there's no mechanism to report that. There's nothing going to prevent you from doing that. So reworking the way that the kernel's own stacks work to use its own virtual memory subsystem has some very significant both security and just debuggability ramifications. The fact that buffer overflows can be detected and reported and explained to the developer, most of which are not security experts, is a really powerful thing. There's quite a bit of complexity here behind this, but it's a very big jump to go from not having this to having this. You no longer have to have the kernel stacks next to each other, so you no longer have to be able to blow past one thing and then screw up some other thing. You can spread them out a bit more. So these are all like kind of things you would be like, wow, how did the kernel not have these before? But nevertheless, things have come quite a long way. And as time has gone on here, the level of sophistication has gone up, the level of focus has gone up. Things are being taken more and more seriously. So past this, we enter modernity. And a big part of modernity is a shift in focus and mindset to the point where a lot of people suddenly care about kernel security a lot. And this is a big reason why. The problem around Spectre and Meltdown, first disclosed I think in 2017, is that there was kind of this big industry-wide panic without a whole lot of understanding of what it actually means. So operating systems were the main place that these classes of vulnerabilities got mitigated. We've talked about CPUs in terms of CPU vendors providing protections, features that enable mitigations. In this case, CPUs are now the enemy. CPUs are now doing things that they shouldn't do that allow attackers to bypass typical protections between privilege boundaries. So operating systems have a pretty big role to play in mitigating these kind of attacks. And the way it typically works is that if you're context switching either from user space program to user space program, or you're context switching between user and kernel, doing a syscall or whatever, then you would flush a bunch of state. So you would clear out a bunch of the CPU's internal state so that it couldn't potentially be deduced from an attacker on the other side. You couldn't potentially influence things. And there have been many attempts to mitigate things in software or with clever gadgets that haven't particularly held up over time. If you want to know more specifically about these bugs, I gave a talk about it last year, if you really want to go into the weeds on these things. But I've never seen more people talk about patching the Linux kernel and who's vulnerable to what than after the Spectre Meltdown era. And if you go to, where is it in the FS? Sys class something. There's sysfs entries that go over all the mitigations. I think LSCPU prints them out, where you can see line by line for what are mostly speculative execution vulnerabilities, what your mitigation status is. But this represented a pretty big shift, I think, and a shift that people tended to accept despite the performance concerns. Intel in particular has taken many gigantic performance hits implementing these kind of things, but something you have to do. Android also, just Android's existence and prevalence and Google's focus on security has also had a pretty massive shift in the level of sophistication of people trying to defend Linux. Android runs Linux, but much like the rest of the Linux ecosystem, it has issues with fragmentation, it has issues with currency, with upstream, it has issues with security. The Android kernel is getting better at being something vaguely closer to upstream, but it's still quite far away. And so an attack vector on Android, you can have all these nice sandboxes, but if you can own the kernel, then you can own the kernel. So a lot of investment in tooling and infrastructure and security came into Linux off the back of Android's prevalence and the ability to target end-user devices that are walking around and connecting to everything relative to hardened servers with a few specific entry points. So I wanted to also mention syscaller. So syscaller is a very sophisticated operating system call fuzzer. It supports Linux and a bunch of other operating systems no one cares about. So syscaller was a big leap in our ability to automatically test the Linux kernel for vulnerabilities. Just being able to fuzz all of the things that the Linux kernel does, well, not all of them, a bunch of them, exposes a lot of problems. And as time went along and things like KASAN and other sanitizers improved the ability that we have to understand what's going on inside the kernel when things go wrong, we get a whole bunch of bug discoveries. Thousands of kernel bugs have been found by syscaller. Now, not all bugs found by syscaller have been fixed and never exploited, but the number's probably on the blue side, I would guess. So syscaller has kind of marked a big improvement in automation, and we do see other fuzzing attempts happening now that never really happened in the past, with a bit more sophistication as well. There's this really good talk in an article about Intel's focus on hardening. Basically, what happens when you're a guest, but you don't trust the host, right? If you're running through KVM, you're a guest of Linux as a host, but you think the host is hostile, and how they fuzz that really early path before syscaller can do anything. So a bunch more tooling and sophistication has come around the kernel that has kind of moved the needle quite a bit. And more and more sanitizers have come along as well. Some of these are really quite new. I think KMSAN only landed late last year. So again, toolchains have had some of these sanitizers for a decent amount of time operating in user space, but increasingly they've been ported to the kernel to do things like KCSAN for concurrency issues that can find data races and whatnot. KMSAN that can find bad memory accesses to the level of you're trying to read from this byte that wasn't initialized in this 64-bit integer. UBSAN for undefined behavior. So our ability to understand what's going on in the kernel is getting better, along with our ability to prevent attacks from inside it. And I also wanted to mention Rust. So I don't know how much of this rant is fueled by Hacker News comments, but people have a lot of misconceptions about Rust, what Rust can do in the kernel, or even what Rust in the Linux kernel is. So I also wanted to touch on that. Rust has like a very baseline level of support in the kernel, to where there's a shim that will let you start writing kernel modules in Rust. And you can do that, and people have done that. None upstream that do anything interesting yet. There's obviously some quite interesting projects in the pipeline, such as the Apple M2 GPU driver. But every time there's some kind of Linux memory safety thing, there's a horde of people saying, oh, if it was written in Rust, this wouldn't have happened. And I love Rust. I am on the Rust evangelism strike force, but I don't really see how it's going to solve a lot of problems. The first thing is that we both can't, and probably won't anyway, rewrite the kernel in it. A big bottleneck for Linux's ability to get better is down to what the maintainers can do, have time for, and understand. Kernel maintainers are overworked. There's many of them, but they have a lot of work to do. They have a huge amount of stuff to keep up with. And learn this entirely new, very complicated language is a pretty tough pill to swallow. Modules are one thing. They're dynamically loaded. They're reasonably isolated within themselves. Rewriting core kernel bits has a lot of woes. Not just in terms of maintainers, but in terms of distributions. Distributions hate changing tool chains. Having to add some new tool chain just to compile the kernel for some like ancient kernel version that RHEL still supports or whatever isn't going to work. So if you're thinking about writing something in Rust today, there's very real problems as to why you might not want to do that. And those problems aren't going to go away anytime soon. So a big part of it is it won't solve all the problems. A big part of the upside of writing things in Rust in Linux is that the problematic bit gets kind of scrunched down. The layer between, the bindings between the C parts of the kernel and the Rust parts of the kernel need to be good. But if you're writing code, if you're writing safe Rust in a module using those APIs, and you probably can't screw it up too bad. But there's still going to be problems. There's always going to be bits in the kernel that are written in C, that are written in pure ASM. There's many classes of bugs that are not memory safety bugs. So that is something to keep in mind as well. And yes, it won't take us to the promised land. If there is a Rust kernel being written, which is quite cool and has come quite a way along. But yeah, it's not a silver bullet, but it will help. Rewriting bits in the kernel will help. There's a whole bunch of abominable things the Linux kernel has to do. If we can just take out all the parts and drivers that like parse strings from users or whatever and just write it in Rust instead, that will make a big difference. But it's gonna take a while. That's about all I had. If you want to know what's gone on after these periods in history, then head to the talk tomorrow. Thank you for watching history, and thank you very much.